Hi, my name is Jamie Knight and my project is titled Extinction Cross-Section Measurements for Single Aerosol Particles Confined to a Linear Electrodynamic Quadrupole Trap. The project will contribute towards improving the understanding of the optical interactions of absorbing aerosol species to help improve current global climate models. Namely, we'll be looking at brown carbon species, which are organic aerosols that both scatter and absorb incident radiation. They're common in the atmosphere emitted via biomass burning and fossil fuel combustion. Brown carbon will be a focus of this project due to the large uncertainties associated with their optical properties. They actually form one of the greatest current uncertainties in global climate models. So aerosols can influence climate in a number of ways. Here we're only interested in the direct aerosol effect, the scattering and absorption of incident radiation. Briefly, two key properties we need to be aware of are the refractive index and the extinction cross-section. Simplistically, they're both related to the amount of light interacts with a particle, and they may be split into their scattering and absorption components. However, it's the refractive index we use in climate modelling. So in this project, we'll use cavity ring-down spectroscopy to experimentally determine the extinction cross-section, and a variation of ME theory will be used to calculate the refractive index. So if we look at the schematic provided, the key components of the cavity ring-down system are the laser, the optical cavity, and the photodiode. The optical cavity is essentially a cylinder with two highly reflective mirrors at both ends. The laser is coupled with the cavity and light intensity builds up within. Light leaks out of the cavity as the mirrors are only 99.9% reflective, and the photodiode detector records the signal. When a threshold intensity is reached, the laser is switched off and the intensity inside the cavity and at the detector decreases over a unique time, known as the ring-down time. The ring-down time would be related to the extinction cross-section value through the equation provided. So why do we need a new approach? Well, single particles must be trapped within the optical cavity in order to interact with the incident radiation. Previous experiments have used vessel beam optical traps, however absorbing aerosol particles are perturbed by the optical trap and are unstably confined, producing inaccuracies in the extinction cross-section values. We will pioneer a new technique during this project to allow stable confinement of absorbing aerosol species. So particles will be confined within an electrodynamic potential minimum created between four parallel rods. This should allow absorbing aerosol particles to be stably confined with relative ease. Finally, ME theory describes the scattering of electromagnetic radiation by a homogeneous spherical particle. ME theory predicts the extinction cross-section and may be fit to our experiment. We may then calculate the refractive index. The values retrieved will be input into global climate models to improve understanding of the influence of aerosols on the radiative balance of the atmosphere. Thank you for listening, and I'll try to answer any questions you have.